How about this? You can see my screen now?
Yeah. Hi, everyone. It's our next webinar, Software Colloquium. And today we have presentation by Dr. Ian Carley. Dr. Ian Carley attained his PhD at Trinity College in Dublin in 2014 with the primary research focus on the radio observations of eruptions and shocks in the solar atmosphere. He then took up a Marie Curie postdoctoral fellowship at the Paris Observatory from 2014 to 2016. While there, his research focused on the use of non-CR radioheliograph to study particle acceleration during solar eruptive events. He is currently a Schrödinger Research Fellow at the Dublin Institute for Advanced Studies and also co-chair of the Solar Key Science Project of the low-frequency array LOFAR. His current research focuses on using International LOFAR telescope to observe flares and eruptive activity in the solar atmosphere. So, Ian, please go ahead, and I will warn you 5 minutes before end of your talk, 45 minutes. So please go ahead. Yeah.
Okay, well, thank you very much, and good afternoon or good evening, everyone. Firstly, I'd like to thank the organizers of this webinar series for the opportunity to provide a talk here today. It's much appreciated. So my name is Owen Carley. I'm a research fellow at the Dublin Institute for Advanced Studies in the Astronomy and Astrophysics section. And I am a radio astronomer. I use low-frequency radio telescopes to study things like CMEs, flares, shocks, shock particle acceleration in the solar corona. In particular, I use an instrument known as the low-frequency array, or LOFAR, some of the images from which you can see on my title slide here. So what I want this talk to be about is just, I'll give an overview about the general phenomena that I'm interested in, particularly in the low-frequency radio domain. And then I will talk about, some recent results that we've had with LOFAR and other radio instruments in studying CMEs and shocks in the solar corona. And then I'll go on to how we use LOFAR right now and going into the future, in coordination with things like Parker Solar Probe and Solar Orbiter. Okay, can I use this? Yes. Okay, so let's get started. What am I interested in? So I'm interested in studying CMEs and CME-related phenomena such as shockwaves. Okay, so this is probably familiar territory to a lot of us, but I'll go through it anyway. So CMEs are eruptions of plasma and magnetic field from the low solar corona into the heliosphere. They carry masses typically 10 to 12 kilograms, speeds, from hundreds to a few thousand kilometers per second, and energies of up to 10 to the 25 joules. So making them, the most energetic eruptive events in the solar atmosphere or in the solar system in general. Usually observed in white light, and this is a particularly nice one. Hopefully this video is playing for you as well as it is for me. This is from Stereo B Core 1, and in the EUV we see from EUVI, you can see, the nascent structure is often imaged in the EUV and its propagation into the heliosphere from coronagraphs in heliospheric imagers and so on. And at the same time as we get one of these eruptions, we have, a whole variety of electromagnetic emissions, of course. For the most energetic of events, you have gamma rays, of course, hard and soft X-rays. We usually use these to classify the flare itself. Microwave in the radio domain, we have microwaves, which are well correlated with the X-rays, and then we have metric and decametric radio waves, and even longer wavelengths observed from space-based observatories. So there's a huge, variety of electromagnetic emission, indicating, there's a lot of particle acceleration going on in the corona. Now, at the same time, some tens of minutes later, if not longer, in situ, what we often see is the arrival of solar energetic particles in the form of electrons, protons, heavier ions, ranging in energy from keV all the way up to GeV for the biggest of events. Just a nice illustration of this I always like to show is this is a CCD detectors, LASCO C2 and C3, and during eruptive events, you will see, the CCD detector being absolutely blasted by particles, during one of these events. It's of course noise in a CCD. It's just a nice illustration of the arrival of a lot of particles at L1, you know, in the aftermath of an eruption. So what am I interested in? I'm interested in, you know, how we go from, you know, large-scale eruptive events to, you know, generating particles and how they propagate on out into space. So the where, when, and how of particle acceleration during eruptive activity in the solar corona, you know, associated with flares as well as with CMEs, and as I'll show and concentrate on CME-driven shocks in the corona. Okay, so one of the best ways to observe CME-driven shocks and particle escape into the corona is in the radio domain. Okay, so in order to describe how we observe this kind of activity in the radio, let's take a look at this cartoon over on the left here. You know, during an eruptive event, we have the solar flare itself. It accelerates particles amongst which the electrons may find themselves on open magnetic field, and they propagate into the heliosphere. You know, as they do so, they generate plasma emission, and because the plasma emission is pretty much only dependent on electron density, as they propagate into the heliosphere, you know, they emit lower and lower frequencies over time because of the lower densities over time. Now, in the dynamic spectrum of, you know, a gigahertz to what we have 0.1 megahertz here, over time, we usually image what we call a type 3 radio burst. So going from high frequencies, swooping down to low frequencies over time, okay? So this is electron escape into the corona. In terms of the shock itself, you know, a CME is a flux rope, and this flux rope can be faster than, you know, the Alfvén speed or whatever magnetosonic speed, and it will drive a shock into the corona. And like all shocks in astrophysics, you know, they're pretty good at accelerating particles, amongst which the electrons will also induce plasma emission, and they will do so in this form here. This is a type 2 radio burst. So again, in a dynamic spectrum of frequency versus time, this particular example is from LOFAR, we have bands of emission drifting slowly to lower frequencies over time. Yes, again, why do they drift to lower frequencies? As I mentioned, you know, typical densities in the corona of density versus height. You know, these are just some of the usual density models we use. We start out at high density and swoop down to low density as we move into the corona. In fact, in the low corona, you can approximate that pretty well with a hydrostatic equilibrium. So as you know, a shock reaches larger height, it encounters lower density and hence produces plasma emission at lower frequencies, hence this drifting feature here. Okay, so from, you know, the drift rate, you know, you can get back at all sorts of characteristics to do with shock kinematics. Some of the fine structure, for example, this type 2 is split into 2 bands. From that, you can get at things like shock compression ratios, shock Mach numbers. So these are actually a pretty lucrative source of information on shock properties in the corona as it's accelerating particles. And as I'll show, you get even more information when you use very fine time resolution and spectral resolution imaging spectroscopy on these things. So just as an example of getting into a little bit of type 2 fine structure, I want to talk about one of my favorite types of radio bursts, and it's a subset of type 2 radio bursts known as herringbones. Okay, so what are herringbones? They're basically a type 2 radio burst in the sense that they have, you know, a drift towards lower frequencies over time, indicating a shock propagates into the corona. Now, at the same time as this drift, we have these fine frequency structures, these streaks here that we call herringbones. Each one of these, you know, streaks or herringbones is a signature of an electron beam being accelerated out of the shock and propagating away. They, you know, and you get these fine frequency structures drifting to lower frequencies and to higher frequencies, an indicator that the electron acceleration is bidirectional in space. At the same time, you get one of these things every few seconds, indicating there's a burstiness and sometimes almost a quasi-periodicity to the shock acceleration itself. Now, there isn't much of a model to describe, you know, why there will be quasi-periodic acceleration of electrons from a shock wave, and I've searched around, and you know, it's not really known what causes these things. So what I'm interested in is, you know, figuring out, you know, well, actually using herringbones as, you know, one of the best sources of information that we have for electron acceleration inside shock waves, because not only do we have the shock acceleration, we also have, you know, the electron beam acceleration that we can see time and again. You know, there's hundreds of these things in the one type 2 radio burst. Okay, so what's some models of the generation of type 2s, or specifically as well, herringbones? It hasn't been really modeled too much in the literature, but some have modeled yes. Okay, thought that was a question, sorry. So some have modeled this, for example, in Schmidt and Kearns in 2012. You know, they model an eruption into the solar corona, and they model electron acceleration on the flank of the CME here. And in particular, it was in a, you know, a turbulent environment leading to corrugated or rippled shock wave, okay, on the flank. You know, this would lead to specific points on this shock wave where you would get a good orientation of your magnetic field, and hence electron acceleration at specific points into the corona. And these would escape this shock as it propagates into the corona. And the shading here is just, I think it's the emissivity one would receive in the radio domain. As well as this, you know, if you have acceleration of electrons on that flank, you might also expect it to be associated with a number of other pieces of activity on, you know, that are associated with the expansion of a CME flank into the corona, namely an EUV wave in the low corona. And if, you know, if we were to actually go and image, you know, the sites of electron acceleration in a type 2 or herringbone radio burst, would we see it here on the flank of an eruption? And would it be associated with the EUV wave? So that's kind of what I want to get at in, you know, studying these phenomena, herringbones, and imaging them with radio imaging spectrometers, basically. There's also been some mention of herringbones in, you know, modeling particle acceleration in terms of ripple shock surfaces, and turbulence has a role to play in this kind of activity, which I'll also talk about later on. Okay, some of the questions that I am interested in answering, where are the shock electrons accelerated that lead to your type 2s and herringbones and so on? You know, what's their relationship with the flare, CME or EUV wave phenomena? Can we tell anything about the shock acceleration mechanism itself? And does turbulence play a role, as it's believed to, in shock acceleration theories? So I'll talk about some of the events that we've studied in trying to answer these questions. So I'll take you back to an event that I published, or I studied in 2013. So this was an eruptive event on 2011, September 22. And we had an eruption on the east limb of the sun that was picked up with a pretty spectacular EUV wave imaged by the Atmospheric Imaging Assembly in 211, 193, and 171 angstroms here in a three-color image. And you can see this nice EUV wave, you know, propagating through the corona. Hopefully that movie plays well enough for you that you can see that wave there. Now, at the same time as we had that EUV wave, you know, there was a whole host of radioactivity in many instruments, both ground-based and space-based. So what do we have here? We have a dynamic spectrum from around 400 megahertz to, 10 kilohertz over time. And we have, first of all, obviously a type 3 radio burst indicating electron beam escape into the corona and heliosphere. If we zoom in here down in observations in the Nancy decametric array and Callisto spectrographs, we see a type 2 radio burst. And over here, if we zoom in, we see again our special herringbone radio bursts. You know, again, these streaks being an indicator, these herringbones being an indicator of sort of bursty electron acceleration happening in a shock as it propagates through the corona. Interestingly, these herringbones don't show a backbone drift to low frequencies, meaning that they're either at a constant altitude in the corona, or maybe they had propagated laterally at a constant altitude. Okay, that's important to note. So the question is, can we do any radio imaging here to try and see, was there any radioactivity associated with this event, potentially on the flank of this eruption? Well, we have particle acceleration features in this Callisto spectrograph here that you can see here. And they just about make it, at least in the Callisto spectrograph, to 150 megahertz, where we can image them with an instrument like the Nantes radioheliograph. So this is what I show here. So again, I show the same set of spectrograms. The white line is an indicator in time. It will play with the movie. Over here, I have AIA 211 angstrom, and we'll see an eruptive event and that wave propagating along the east limb towards the south here. There's two radio sources at 150 megahertz here, one associated with the flare itself, and one that will propagate in tandem with the EUV wave as it goes southwards, okay? And the color grading of those contours change, showing that the brightness temperature reaches up to 10 to the 9 Kelvin, and these are clearly non-thermal radio sources here. Okay, so one of the sources propagates southward along with that EUV wave, disappears for a little bit, and hopefully you can see that it appears again on top of the wave at the same time, okay? We play it again. It propagates towards the south, reaches quite high brightness temperatures, and comes up again at the EUV wave site. Okay, so I was pretty interested in this because it's an indicator of at least a non-thermal group of electrons generating what we think is plasma emission on the flank of the CME at the same time as you see, an MHD disturbance in the EUV. So are the two related? So first of all, kinematically, what we did was look at their propagation and position angle of both the radio source and the wave, and this is what I show here. So this is position angle with respect to time here. So we have the EUV wave in pink at 1.27 our sun, propagating at around a speed of around 480 kilometers per second. The black crosses here are the radio sources propagating at the same time, and you can see they pretty much propagate in tandem together. They follow the same position angle change as that CME expands into the corona at a somewhat similar speed at the same height. Okay, so there's a clear kinematic relationship between the two, and I'm interested in what that kinematic relationship is. Is it related to that idea that you could have particle acceleration on the flank of that CME? We're actually seeing that electron acceleration in the radio, and then we're seeing, some manifestation of that disturbance in the EUV here.
And
so first of all,
could you tell again what is CBF?
Oh yes, I should have said this at the time. There was many acronyms used for EUV waves. We call this a coronal bright front at the time. Because this was, I think we had done a few papers that gave it a CBF, but it's actually an EUV wave. Sorry, I should have pointed that out. That's the numerous acronyms that these things can take on. EIT wave, EUV wave, CBF, it's the same thing.
Great, thanks.
Okay, so what do we want to find out here? Is it possible that there's a shock in this region of the corona at that CME flank? Well, one way of kind of testing this is to see, compare the kinematics of the source and the wave to the Alfvén speed in the corona to see, did it travel faster than the Alfvén speed? Okay, so what do we need to do to get the Alfvén speed in this region? We need a measure of the magnetic field, and we need a measure of density. Okay, so firstly, what we did was try and get an estimate of the density in the plane of the sky using SDO from a differential emission measure map. I'm making some assumptions about how much emission we have along the line of sight. We're able to get a density diagnostic from 1 to 1.3 our sun. Now from 2.5 to 5 our sun, what we did was use LASCO C2 polarized brightness measurements, from which you can also get density measurements. And in between, in that gap there, at each position angle, we actually just fit a hydrostatic model between those two data sets to come up with a complete density map in the sky plane with density values you can see here. That's what the color grading is. And then what we did was we took, in the same sky plane, from a PFSS extrapolation, is a measure of the magnetic field. The combination of the two will give us a map of the Alfvén speed in the sky plane. And this is what I show here. So the color grade is Alfvén speed, starting down in hundreds of kilometers per second to thousands, as we would expect. So for example, You would expect it to be thousands of kilometers a second in an active region, but we see some pretty interesting features here. These holes in the Alfvén speed, or these minima in the Alfvén speed, right next to the active region. You see one here and you see one here, where it actually drops to about 100 kilometers a second or less. And if you were to propagate a disturbance through this region at 500 kilometers a second, as we see, it would almost definitely drive a shock in that region. So there's good evidence to say that it was fast enough to be associated with a shock. Just as a brief aside here, I like to compare this to some of the modeling work that was done by Wormuth and Mann in 2005. Here's the limb of the sun here, and they have an active region embedded in the dipole field of the sun, and kind of evaluating the Alfvén speed. I think this is either the plane of the sky or the ecliptic, but it's pretty similar. And depending on the orientation of the active region, you again have these minima in the Alfvén speed, through which if you drove an eruption through there, it will be very easy to drive a shockwave because it reaches such low values. So this is just a good comparison between an Alfvén speed map we produce from data and one in modeling showing pretty much the same thing. So it's always good when the models and the data show similar features. Okay, so what was the interpretation at the time of this event? So what we thought was we have a shock driven laterally into the corona on the CME flank. The low coronal manifestation of this is the coronal bright front or EUV wave, whatever we want to call it. And then the electron acceleration itself being associated with this non-thermal radio source. Well, at the time, this wasn't without its debates about what that radio source was. If you're into type 4 radio sources, a lot of people said this is a stationary type 4, this is a moving type 4. It's not really associated with a shockwave, okay? But what we did say, it's associated with energetic electrons in a region where it's likely to have a shock at least. Now, some of the controversy, I guess, was that, we only have one radio source here. We can't really image a herringbone. We can't image the propagation of electron beams to see where they're escaping into the corona. To do this, we would need more than what the non-stereo radioheliograph offers. And it offers just discrete frequencies, okay? And here we just have 150 megahertz. So what we'd like to be able to do is full imaging spectroscopy in a herringbone radio burst, enabling us to image any feature we want in a dynamic spectrum and potentially in a herringbone image its propagation or escape into the corona. So this is what leads me on to modern instrumentation. Okay, so how do we do it these days? So this is the low frequency array, or LOFAR, the instrument that I use these days. So LOFAR is an international, it stands for the low frequency array. It's the International LOFAR Telescope. It operates between 10 and 240 megahertz. It consists of 50, maybe plus stations spread across 9 European countries, going from our station here in Ireland in Birr into the UK. There's one in France. I think there's 6 in Germany, the Netherlands, Sweden, Latvia. There's 3 stations in Poland, and there will be a newly built station in LOFAR Medicina here pretty soon. This one isn't operational just yet. Okay, so each station sends basically data at high rates via fiber optic link to a central hub in the Netherlands, where the data is beamformed and correlated across the entire array in this pretty strange looking building here. This thing generates around 7 petabytes per year, which is an enormous challenge in data storage. It's a challenge in data science, and we do have a few applications in machine learning because the data rates are so big here. It's not, of course, a dedicated solar instrument. Okay, so it has a number of what we call key science projects. Some of the more popular ones, I guess, are epoch of reionization and cosmology studies. There is the LOFAR 2-meter sky survey, pulsars and transients. There's AGN. It does many things. The solar and space weather key science project is headed up by Pietro Zucca and myself, and we as a group from many groups around Europe and beyond We write proposals for time to observe the sun and basically decide the scientific, I guess, solar scientific remit of the telescope. What does a LOFAR station look like on its own? So in and of itself, a LOFAR station is a radio telescope. It's an interferometer. This is our one at Birr Castle in Ireland. So it basically consists of a field of antennas. So we have a field of what we call HBA tiles, 96 of them. Inside each tile is a cross dipole, 16 cross dipoles, and this array basically sees from 110 to 240 megahertz. We also have what we call low band array tiles, seen from 10 to 90 megahertz. Okay, and it's it's actually extremely basic at the front end. The antennas themselves, especially for the LBAs, are just cross dipoles. They're just wires basically above a ground plane metal grid that you would pretty much the same as you would find in reinforced concrete actually. So the dipoles are attached to a small preamp up here, and they send their signals via coax cable into this container here that contains 192 receivers and all the beamforming capacity to point our phased array in particular directions on the sky, which I'll talk about in a second. So yeah, it's an all-Ireland endeavour. We have many universities, 4 in Dublin, there's NUI Galway, 1 in Cork, Athlone, and then there's a Armagh Observatory in Northern Ireland. So it's a kind of a Northern Ireland Republic kind of combination of universities from across the entire island of Ireland that operates this thing. Yeah, brief aside here, we do use it, or this station is used as part of the entire network, but we use it as a standalone station as well to observe many things. We have a purpose-built high-performance computational backend on the back end of our telescope that we call the Real-Time Transient Acquisition Cluster. It's basically a bit of a monster cluster of a few Dell PowerEdges, capturing data at very high data rates at 5 microsecond sampling, so that we can produce what's basically very high time resolution dynamic spectra to look at solar radio burst fine structures, pulsars and transients. There's SETI research with this thing, with the Breakthrough Listen Foundation. And we also use it as a platform for deep learning, automatic detection of solar radio bursts, which is kind of an ongoing project there. And it generates data at a rate of about 4 terabytes per hour. So this thing is a bit of a, LOFAR in general is a bit of a headache with the amount of data that it produces. Okay, so enough about the single station. So how do we use LOFAR to observe the sun? Well, primarily what we do is we use the Dutch stations only. We only use the Netherlands stations, the core stations in the Netherlands, and what we call remote stations, which are still in the Netherlands. So we have 36 core and remote stations that we use as an interferometer to observe the sun. We have, use it for interferometry. This is just a nice example of observing the 2015 March 21 partial solar eclipse in the radio domain. This is multi-frequency synthesis imaging from 140 to 158 megahertz. You can see the quiet sun, and hopefully you can see the limb of the moon there during its egress during the eclipse. And this is, you can see this published in Ryan et al. 2021, in which we actually used the limb of the moon to try and resolve smaller structures than would be normally available through standard interferometry. Okay, so we do use it as an interferometer, but I want to talk a little bit about how we use it in different observational capacities. I want to talk about what we call tide array beam imaging mode. Okay, so this isn't interferometry. It's not the production of visibilities. There's no cross correlation going on here. What we do is we take the signals from all stations and coherently sum them. We don't correlate them. Okay, what does this allow you to do? You can sum them in any which way, but what it allows you to do is point beams, digital beams of the telescope in any direction you want, and almost as many beams, independent beams as you want. That's only limited by computational capacity. So this is just an illustration of LOFAR being able to observe an object in this direction, here and here, all simultaneously. But what we can do is take 200 plus beams and arrange them in a honeycomb pattern, like you can see here, at the target source, which is the sun. What does this allow us to do? Well, each of these beams provides us an independent dynamic spectrum, okay, completely independent from the others. What this essentially enables you to do is produce imaging spectroscopy, by making an image out of these beams. The key feature here is that you can do this at really, really high time resolution and really high frequency resolution. In fact, you can do this with 5 microsecond time sampling, which is probably some of the fastest imaging spectroscopy we can do in solar physics. But usual observations, usually just to save on data rate and have better frequency resolution, we can get 5 millisecond imaging basically, with this frequency resolution, meaning full imaging spectroscopy in 10 to 90 megahertz, allowing us around 6,500 frequency channels across this observing range at very, very high time resolution. So what does this look like when we observe the sun? Okay, so what images do we produce with this imaging mode? So I show here the publication from Diana Morrison that we did back in 2019. And this event is pretty famous right now. It's the one from 2017, September 10, in which AIA imaged pretty much, the prototypical or very typical looking flux strobe. It almost looks like the standard model of eruptions, and many papers have been written on this one here. So at the time LOFAR was observing, we were in tide array beam imaging mode. And this is just one dynamic spectrum that I showed here. So 30 to 55 megahertz and 40 seconds of data. And interestingly enough, what we managed to pick up was herringbone activity. Okay, so again, this is a signature of a shock related to this plasmoid eruption. And this time, we're able to actually directly image anywhere we want, all of the herringbones if we want. So each one of these things, these streaks here are herringbones is a particle beam, electron beam being accelerated out of the shock, and they're bidirectional as well. One of the big problems with radio imaging spectroscopy is that you can image every single pixel within this dynamic spectrum, and even with just 40 seconds of data here, we have 12 million images to choose from, which I guess is a good thing, but it's also a bit of a curse to have that much data. But initially, okay, we take it easy. We just image a few radio sources here associated with these herringbones. Okay, so this is a SUVI image and LASCO C2 showing this nice eruption here. Okay, and we have a radio source at the front where we would probably expect the shock to be driven. And again, like the NONSE study, we have these herringbone radio sources, or at least electron beams, on the flank of the CME. And this time what we're able to do is image them from high frequencies to low frequencies, so from 50 to 35 megahertz, where we can actually see the propagation of that beam on the flank of the CME. So this is kind of highly related to the modeling work that I showed before, saying that this is where you would potentially observe herringbones, and this is kind of a confirmation that this is where we are observing them. So I did a bit of data-driven modeling here for this event, in which I take a PFSS extrapolation. I go through the same procedure as before of producing an Alfvén speed map, this time deprojecting it off the sky plane to produce, 3D Alfvén speed surfaces. And what we have here is a forward modeling of the shock bubble itself and the imaging of the radio sources themselves. So what does this tell us? So we have, the electron acceleration of the beam on the flank of that shock. It was in a pretty low Alfvén speed environment, a few hundred kilometers per second, in an open magnetic field region where these particles are going to escape. Okay, so this is actually, it shows you what a lucrative source of information full imaging spectroscopy of herringbones actually is. We can actually see where these particles are accelerated and where they escape to. Other characteristics, we were able to get beam speeds or beam energies, I should say, of 34 keV by comparing, the propagation of that flank and the Alfvén speed, work out Mach numbers of around 2.5. And the shock geometry was quasi-perpendicular, which actually has consequences for the kind of acceleration mechanism one would expect for that geometry, namely shock drift acceleration. So it's, there's so many things we can tell here. But can we do anything more? So I mentioned LOFAR has, really great spectral resolution and time resolution. So can we, dig in deep into the fine structure of these herringbones, possibly an indicator of something a little bit closer to the acceleration mechanisms themselves, actually. So this moves me on to, digging into the fine structure, and by way of motivation, I just want to point out two studies here that have come out recently. We have Magdalenic et al. In 2020, LOFAR radio bursts that I actually showed at the start. The crux of this study is that when we zoom in to various parts of this type 2, we see a huge range of fine structure, which does not yet have a classification. It's almost, we don't really know what causes all of this stuff. So what do we see? We see things like herringbones, that may be an indicator of electron acceleration. And we see fragmented types of radio bursts. Who knows what it's from? It could be from, the corona being inhomogeneous. Is it from turbulence? We also see, I want to point out this study as well, from Chen et al. In 2018. So this is from a type 3 radio burst, and they did something pretty interesting here. So what they do is they take the intensity values with drift rate from a type 3, which is an indicator of electron beam escape, and they get flux versus distance using a density model. Then what they do is they take this intensity variability and perform a power spectrum here. Now the power spectrum produces a power law, which is pretty interesting because it produces a power law index of minus 1.71, which is almost exactly, it exactly matches the minus 5/3 that one would expect of turbulence in the corona. And in particular, what causes this is density turbulence. So this got me thinking, can I apply this technique from, what's a type 3 radio burst to a type 2? Can I go ahead and diagnose not only particle acceleration features in a type 2, can I also diagnose turbulence at the same time, which has consequences for the acceleration mechanism? Okay, so to do this, I used a new instrument, or relatively new instrument, called Nenufar, which is the new extension in Nancy upgrading LOFAR. So this is an extension to the French LOFAR system, which you can see down here, and looks exactly the same as the Irish one. So what they've done here is they basically extended it with mini arrays, and these mini arrays contain 19 LWA antennas scattered around the French LOFAR station, within a diameter of around 400 meters, and a few outlier stations that we see here. Okay, so the interesting thing about Nenufar is that it's used as a LOFAR backend, a LOFAR superstation. It's also used as a standalone beamformer and basically an imager as well. So it's in its early science phase actually, so we don't yet have 96 of these mini arrays, but we're kind of commissioning observations, and it has a number of key science programs like LOFAR, not solar dedicated, but we've recently set up the Solar Key project with the aim of defining how we can use this thing for observations of the quiet and active sun, basically. But myself and Sophie Masson at the Paris Observatory are, I guess, co-principal investigators of that key science project, or key project. Maybe this video will play, it's pretty high definition, so I'm not sure how well it will transmit. But this gives you an idea of the scale of Nenufar. It's just a flyby showing these groups of LWA antennas grouped into mini arrays. These are beamformed and then digitally beamformed, on whatever target we want, and we use it for the sun. Okay, so one of the first events that Nenufar picked up is a pretty interesting one. This was in 2019, March 20. We have eruptive activity that we observe in AIA, and we have a nice EUV wave here. There was a C 4.8 class flare, which is not the most impressive flare in the world, but we have a huge complexity of radio bursts picked up with Nenufar again in our dynamic spectrum here. So what we see is something that's pretty difficult to classify actually, but we have a type 2 radio burst here, okay, that you can see drifting here, that I've split into 3 separate radio bursts, or 3 separate type 3s, okay, but they're the one type, sorry, 3 separate type 2s, they're the one type 2 radio burst. So Nenufar, like LOFAR, has really excellent frequency and time resolution. So if we zoom in into one of these radio bursts, again, you can probably guess it starts to get us at herringbone fine structure, okay? So again, we have our type 2 indicating a shock. We have the herringbones indicating electron beam escape into the corona. And they do so at around with an energy of around 20 keV. And I do the same here as the CHENELAB study. Okay, so I take an intensity versus frequency, get intensity versus distance, and take a power spectrum of this. This is what we see here. And what we see is a power law with an index that's remarkably close again to that 5/3 value. So this is a pretty new result. Okay, so this is a simultaneous measurement of shock properties, of electron beams accelerated in that shock, and density turbulence all at the same time. And, you know, given the fact that turbulence in general may be, you know, a key component in the electron acceleration mechanism, it's a nice diagnostic to be able to make, and one that I hope to do again in the future as well.
5 more minutes.
Okay. Say again?
5
minutes?
Mm-hmm.
Okay, yeah, I will hurry up. What do I have here next? Yes, so we had no imaging, but what I did was a bit of forward modeling here. Obviously, the shock bubble, you know, embedded this in a magnetic field extrapolation, you know, kind of giving you an idea of where the electron acceleration took place, and an illustration of what kind of mechanism would cause these features here. So electron beam acceleration into a turbulent environment, basically. Okay, this is in Review and AppJ. Okay, so this takes me on to how we use LOFAR these days, and what we're doing currently, and what we'll do, how we'll use LOFAR to observe in the future. Okay, so the current spacecraft that we have now, I'm sure we're all familiar with, Parker Solar Probe and Solar Orbiter. They represent a great opportunity for ground-based support and coordination, you know, during the perihelia of these spacecraft. So PSP will perform a number of perihelia down to 9.9 our Sun. Solar Orbiter and ESA mission will perform its perihelia down to 0.28 AU, and they both carry on board, you know, in situ and remote sensing instruments, giving us, you know, the scientific remit. You know, we want to study eruptions, eruptive events, particle acceleration, and so on. So it's a great opportunity at the same time as these spacecraft are performing their in situ observations and remote sensing as well. We can observe at LOFAR. So what have I plotted here? The red line, you may have seen this plot before, is the distance of Parker Solar Probe over time from the Sun. And during each of the perihelia, for example, this is 2018 to 2019 and some 2020 perihelia here, we have been observing with LOFAR for around 2 to 4 weeks during each of these perihelia. And it's the whole system that we're dedicating to these observations. So, you know, core remote and international stations to do imaging in both tide array imaging, interferometric. We have interplanetary scintillation studies as well, Faraday rotation studies. So, you know, the whole remit of observations one can do for LOFAR, we're doing it at the same time as these perihelia. And as well, the upcoming ones in the following year, you know, we'll have a Solar Orbiter in tow as well. During the first few perihelia, I'm sure you're all aware that, you know, the Sun wasn't particularly active when Parker Solar Probe was actually making its close encounters. Typical observation would have been active regions on disk without much activity. So, for example, this just shows that the, you know, X-ray activity was pretty much nothing during these days. But interestingly enough, with NENUFAR and LOFAR, we pick up hundreds and hundreds of Type 3 radio bursts, indicating there's electron acceleration going on in these active regions without any indicator of an X-ray counterpart. The question is, what's causing this continuous acceleration? It's something that I hope to look into in the very near future here. So we have actually quite a large archive of data of this type for each of the Parker Solar Probe perihelia that have already taken place. This is just one of the research one of the pieces of data that has been published from that era. This is just from Peijin Zhang, showing a nice Type 3 radio burst in one of these noise storms being imaged in both fundamental and harmonic, and using this as a diagnostic basically of turbulence. So Sorry, I have to quickly go through this. Okay, so future observations. So as I said, this is one of my final slides here. LOFAR is not a solar dedicated instrument, but we do have a current design study funded by the European Commission to try and design or design an upgrade to LOFAR to transform it into a space weather and solar physics instrument that can provide you with routine observations of the sun and heliosphere. Okay, so this is the entire system that needs to be redesigned, from front end antennae, station electronics, to central processing, to pipelines. What we hope to have is 2 data streams running through the entire system. You know, the red one here giving us space weather observations, and the blue one here, the radio astronomers can do what they want to do simultaneously, and we don't interrupt each other. So if you're interested in finding out more about this, you can find more at lofarforSpaceweather.eu. I think I may end with this one because I'm out of time. What do we hope to do? Well, everything that I showed before in monitoring solar eruptive activity, in imaging and in spectroscopy, interplanetary scintillation studies, like you can see here, doing tomography of the interplanetary medium, and ionospheric scintillation studies. So measuring, you know, the whole range of space weather activity from the sun to the heliosphere, to the ionosphere. And yes, so if you're interested, please do visit that website there. Okay, so I'll leave it there, and I'll leave on my summary slide. Hopefully I've convinced you LOFAR is a fantastic image to be able to observe shock particle acceleration on the sun. And we're just digging into the data now, and we've plenty of more data to dig into with our ground support of Parker Solar Probe and Solar Orbiter as well. So thank you for your attention.
Yeah, thank you, Ian. It was really very interesting and I enjoyed. So we are open for questions and discussion. So please either unmute yourself and ask question or raise your hand, and I will invite people to ask question, make comments. No questions? Bin?
I see Ben has raised his hand.
Jim. Bin is unmuted, so and then next Jim, I think, yeah?
Okay, thanks. Fantastic talk, Ian. Thank you very much. So I have one quick question about your polar spectrum of the herringbones. So,
yes.
So this is the intensity versus frequency translated into intensity versus heliocentric distance, basically.
Yes.
In order to have accurate intensity, you guys must have done very accurate bandpass intensity calibration. I'm wondering how this is done in practice.
Yeah, so what we unfortunately, these observations were not calibrated in solar flux units. In fact, we didn't have any calibrator observations at the time. So what we did was take quiet time spectrum and divide through with the quiet time spectrum, essentially flattening the whole thing, making sure that any intensity variability was not due to the response of the instrument. It was actually due to intensity variability in the radio burst itself. So unfortunately, it was the only question that I could, you know, that's legitimate. It's not calibrated, but the best we could do was flatten the entire spectrum with quiet time observations.
Thank you.
Thank you. Okay, Jim Drake, please go ahead.
Hi there. Very nice talk. Enjoyed it. I have a question about the very end of your talk where you talked about that active region on the disk, and you were commenting that there was, what, thousands of type 3 bursts, a very large number of type 3 bursts.
Yeah.
Yeah. So my question is this: were you able to then figure out the spatial localization of these bursts? Where were they with respect to that that active region? And I'm interested in this because, you know, one of the things we're talking about and thinking about is how energetic electrons actually escape after undergoing magnetic reconnection, for example, and acceleration. And so I think
Sure.
trying to visualize where these energetic particles are coming from would be extremely valuable.
Of course, and the really nice thing about this data set, I've just showed the dynamic spectrum here, but we have full imaging spectroscopy with LOFAR as well. So for sure, on my current to-do list, even for next week, is to start on that imaging, and I expect to see a number of radio sources above that active region, giving us an indication of where and when those electrons are escaping, if not accelerated, in the corona. So yeah, so this is definitely a thing that I want to do, and I think it will give a good indication, of, as you say, of where they're accelerated and how they escape. Particularly if we do a field extrapolation and see, if there was some open field there, for example, we may be able to get an indicator of how they're escaping. In fact, maybe I can show you in one of my backup slides here. This is one event in particular. It was a noise storm on a different day. Hopefully, can you see this? Yeah.
Yeah, I see it.
Yes. Okay. So we have wind waves, stereo waves, Parker Solar Probe, and LOFAR all was imaged the same Type 3 radio burst. Happened to be part of one of these noise storms. One of them in particular, Sam Badman of UC Berkeley did triangulation. Here's PSP wind and stereo of how this Type 3 is escaping into the corona. With LOFAR, what I was able to do is image the radio sources and come up with a deep projection off of the sky plane and see where the radio sources were. Okay, well, there's a good bit of uncertainty of their position, but they're where you expect them to be. When you do a field extrapolation, they're in the open field, meaning that they're accelerated here and they're escaping into the corona. In this study in particular, we want to see where they escape and if they're detected by stereo. But I can do this time and again, hopefully, for the many hundreds of Type 3s that we see in that observation, to see, do we see something of the same kind, So I think it's a really nice data set to have.
Great. I look forward to hearing about this in the future.
Sure. Thank you.
Can I ask a follow-up question about this? Very quick.
Yes. Yeah, sure.
So the dynamic spectrum you show here is pretty narrow band. Do you think this is a high resolution version of the Type 1 noise storm, or do you think those are Type 3 radio bursts, storm of Type 3s?
Yeah, this is something that's unclear to me. So how well correlated are Type 1 storms and Type 3 storms? I mean, as far as I'm aware, Type 1 storms, they do indicate particle acceleration going on as well, somewhere in that active region. My feeling is the Type 3s just indicate the escape of those particles. So if I were to, say, look above 100 megahertz, maybe an Orphée spectrograph that would have been observing at this time, I may expect to see a Type 1 storm, which are those narrowband features that often come simultaneously, So yeah, I think there may be an opportunity, if there is a Type 1 storm at higher frequencies associated with this stuff, we could image it with the non-stereo radio heliograph as well, which became operational again recently. Hope that answered your question.
Yep, thanks.
Okay, Dale?
Yeah, Owen, I had another question related to that, I guess, and that is that LOFAR does have the higher frequency band.
Yeah.
I haven't seen much published about solar results from that. I'm just wondering, obviously it would give you higher resolution. There are different kinds of bursts there. Type 2s are certainly much less likely, but I don't know, does the tide array format work in that high band, or is it?
Yeah, but both types of imaging do. And one thing I should point out, actually, so LOFAR, I said, consists of these HBAs and LBAs. We can't use them simultaneously. So that's, firstly, the reason why. Using the low band array more so, I guess, is a bit of a hangover from the times when we had the non-stereo radio heliograph. So we thought, well, we have imaging in that range, let's do the lower stuff. But I think we do need to return to it again for sure, because it offers you better spatial resolution, obviously, and we can do all the same types of imaging that we can in the low band array. So yeah, that is a plan for the future for sure in both types, both the interferometric and this tight array. I should say as well, related to this, the LOFAR for Space Weather Project makes part of a general upgrade to LOFAR known as LOFAR 2.0. And I think I have a backup slide of this as well. LOFAR 2.0 aims to have the ability to image or do any kind of observation in both LBA and HBA simultaneously. So whereas before we had to pick one or the other, at this time, you know, with the upgrade, we'll be able to do both at the same time. And that upgrade for the Dutch stations is actually going to be rolled out pretty soon. So we should have, you know, from 10 to 240 megahertz imaging altogether simultaneously, which would be pretty nice.
But in that case, are you able to steer the beam separately so you can, because you need a
Sure.
tighter array of beams for the high.
Yeah, so with the addition of both HBA and LBA at the same time, you need extra beamforming capacity, meaning we need more beamformers in those cabinets, and that's part of the design. So, you know, usually we have 488 beamlets. We're going to have double that with the LBA HBA. So hopefully we'll be able to do both at the same time, yeah. And the central correlator, which is a GPU cluster, has got an upgrade in anticipation of the increased data rates that will provide as well.
So just what you wanted, more data.
Yeah, double the amount of data, more headaches.
Okay, I don't see any other raised hands, so may I ask?
Gregory, can I ask? Oh, I'm sorry, Gregory. Go ahead. You ask your question. I was going to ask a follow-up.
Okay, I just want to ask a question: how you decide the spacing between your beams? Because, for example, you select a frequency and you select sort of a spacing following like Nyquist criteria, and then at higher frequencies it will be like holes, and low frequency beams will overlap. So, what is your strategy in selecting this?
Yes, well, I think the strategy is not to have the beam overlap with the next one, but they slightly do. This causes spilling of intensity from one beam to the other sometimes, and we're kind of still investigating that. It may spread out a source bigger than it may seem. Yeah, so it's basically to avoid overlap. Sometimes we have them slightly more spaced out, just to avoid that overlap, basically. So yeah, that's how we do it.
Throughout all frequencies, or what?
The spacing would be determined independently with frequency, yeah, I guess. Because the beamforming itself would depend on the frequency in the correlator, how the delay and the phase delays you apply to produce the beams are independent in each frequency channel, so to speak.
Okay, thanks. Jim?
Yeah, so just, I think, sort of a follow-up on Dale, and I apologize for asking a dumb theorist question, but would going to higher frequency, like you're talking about, also allow you to do imaging on lower altitude in the corona and maybe closer to where the active regions are?
Sure. Yeah, that would be the idea. It would be the activity that's kind of maybe a little bit earlier in the event, as opposed to seeing it when the CME has already emerged into C2. You might get, you know, the very early stages of activity in the low frequency domain. Depending on what's there, you know, you can see all sorts of low frequency radio events, you know, type 2s or type 4s. It would just depend on what was taking place. In the higher frequency domains.
You keep mentioning over and over shock. So, I mean, some of us are actually interested in the reconnection process and particle acceleration. Is there a reason I mean, I realize that the type 2s are normally associated with shocks, but if you're now going to type 3s, I mean, shouldn't we be probing then the reconnection acceleration process also in a more direct way?
Sure, for sure. And I realize I think this seminar series is more to do with the solar flare and reconnection particle acceleration. But in the higher frequencies, yeah, you can get at, you know, the reconnection events in the early stages of the flare itself. And with LOFAR's, you know, extremely good time and frequency resolution, I assume when you zoom into those events, you're going to see an awful lot of fine structure to do with the particle acceleration itself, if not the plasma instabilities that generate the radio emission. And doing that at higher frequencies, like you say, will get you lower down in the corona, closer into that, you know, the early stages of the event.
Okay, any other questions or comments? Chile?
Okay, just question. So because this LOFA has a large frequency coverage, even especially a low frequency, would that help to, because in some of this discussion in the solver, there's sometimes the discussion of the electron transport, and with a larger coverage, would that be able to cover the energetic electrons transport outwards and be able to answer some of the questions related to that?
I guess so. And I guess this brings me back to this study again. You know, 30 megahertz is about as low as we can go for low fire imaging, maybe 20. And that would get you to type 3s and beams that have escaped. You know, you could image them when they're at, let's say, 2 or 3 our sun. That's about all we could do. And beyond that, of course, you have to use the space-based observations. So in terms of their escape and their transport into the corona, like this study, yeah, we can do that for sure. But we can only go so far, and you know, obviously not as far as the interplanetary stuff. I hope that answers your question.
Right. I guess the group 5 would be interested in that. Somebody else may comment on that too.
Sure.
Any other questions or comments? I don't see any raised hands or unmuted microphone. So let me thank participants in the speaker, and let me make a brief note that formally next webinar would be scheduled August 18th. So far the slot is empty, not taken. So we can either go to vacation during this slot, or I invite nominations or volunteers to give a talk on that particular slot. So please let me know if any nomination or self-nomination is available. Okay, so thank you very much and see you next time. Yeah.
Thank you, guys. Thanks for your attention. Thank you.